Good morning. So at the last lecture, we had spent some time looking at the E field surrounding a disk of charge, and we said this is a really useful example to think about. It's a good benchmark for thinking about how electric fields work and how to carry out integrations. So the disk looked like this, and when I had gone through and solved for the electric field along the axis, I flipped this so it was along the x-axis. We had come up with these formulas, one written in terms of total charge, one written in terms of charge per area, and I had suggested, and I'm still going to assert, that both of these formulas are useful. So I want to keep both of them. Now, we had written out, I had graphed this and shown just how rapidly the electric field is going to drop off from this flat circular disk of charge and compare it with a point charge. So in the point charge case, as we get closer and closer, the electric field is going to approach an infinite value, and we said there are no actual point charges. At some point, with every object, you reach a surface and the electric field is still finite. So you don't have, if you're going to lose sleep over the existence of point charges, don't lose sleep. Get a good night's rest. We don't have examples of point charges. It's an approximation that we use for the mathematics. And this is what that graph looked like. And then we said what we wanted to do was look at, here is the disk turned sideways. We spent some time talking about why at the surface we don't go to zero. And that's because we don't go right inside the charged disk. We imagine the charged disk is infinitesimally thin, so even as we approach x equals 0, that just brings us right up to the surface. And so we get a finite E field right at the surface, but it drops off, as you saw, really rapidly. We said that, if 1 represents the electric field at the surface, actually 2 pi k sigma, one of those, then here is 80% of that in 60, 40, 20. And we said that by the time x equals a, where a is the radius of the disk, we've dropped down to 30% of that peak value. And we said that, if I took a 10 centimeter disk, that would mean the radius would be 5 centimeters, a would be 5 centimeters. So if I take a 10 centimeter disk and I come 5 centimeters away from it, the E field has dropped to 30% of its peak value. That's a really, I think, rapid drop-off. Now, we want to spend some time looking at the other limit, and the other limit is what happens when x gets much, much bigger than a. Now, you're going to say, okay, if you get far enough away, the E field's 0, but that we don't want to think in those extreme terms. What we want to say is, as we get really, really far away, is there a version of that formula that would specifically apply at large distance? So the way we deal with this is to use approximation techniques. Now, again, in your calculus classes, remember doing those chapters on series? And kind of, once you had developed different ways of approximating functions using series, you could take things like sine functions and cosines and tangents and exponentials and logarithms, and you could write them as a series. Now, those are useful techniques in physics and engineering. And so when you look at Appendix A in our textbook, all of the mathematical formulas, one of the sections back there actually takes commonly used functions, sines and cosines and exponentials, and writes down a series of ways that we can, or writes down a formula where you can write those expressions as series. Now, why would you want to do that? When we have an expression like this that's pretty complicated, you know, x over a squared plus x squared to the half, we can plot that. But it would be nice to know what that looks like for a particular region. Again, if we look far, far, far away. And what we've been suggesting is that once you get far enough away from any charge distribution, it starts to look like a point charge. So we want to just check and see if we can verify that. So here's the plan. What we're going to do is take this expression. Now, the complicated part of that expression, I am going to claim is, let's see where we are here. I am going to start with this expression, the x over a squared. I'm going to start with it right here. So x over a squared plus x squared to the half is x times x squared plus a squared to the minus 1/2. And that says that this expression then can be written as 1 plus a squared over x squared to the minus half. Now, why did I take this expression and write it this way? Well, because back when I was learning approximation techniques in my calculus class, when I was looking at series, it turns out one of the most useful approximation techniques is to take any expression, 1 plus u to the n power, where u is much, much less than 1, and I can write that as 1 plus n times u plus, and then there's a whole series. And you can look in the appendix and see this, or you can look in your calculus books. Well, that says that whenever we run into something written as 1 plus u to the n, that could be approximated as 1 plus nu if u is really small. These successive terms in this expansion are going to be u, u squared, u to the third, u to the fourth, and these higher powers of u are going to get smaller and smaller. So what that tells us is to approximate this expression, I can just keep the first couple terms. Very likely that's going to be enough. So I did that. What I did was take this expression and write it so that it looks like this. I'm trying to make this expression look like this so that I can use the approximation. So it does look like that, and u needs to be really small, and a squared over x squared is going to be really small because we said we're going to be looking at distances that are much, 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 really much larger than the radius. So this now becomes my little tiny piece, my u, and the power I have here is minus 1/2. So this approximation formula works for positive and negative power expressions. So I can take the 1 plus a squared over x squared to the minus half and replace it with 1 minus 1/2 a squared x squared. Now, there's more terms in that series, but they're going to be so small, I can just ignore them. And that says that this expression up here can now be replaced with this expression, because the 1 that I had here will cancel the 1 here. There's a minus sign, that the two 1s are going to cancel out. When I use that minus sign with this minus sign, that flips the sign, and so I'm going to keep 1/2 a squared over x squared. I'm going to ignore smaller terms. The leading term canceled. So the 1s cancel, I keep one additional term, and I ignore the rest. And what that gives me is an expression for the E field as x gets really, really, really large, and look, it's a point charge. So we've established that mathematically a disk of charge, as you get far away from it, the E field converges with the E field of a point charge. The formulas become more and more similar as you get far enough away. That has to happen for every distribution we look at. Some are easier to show, some are more more difficult, but for any distribution, it has to be the case that at large distance, those will converge. Okay, it worked. Now, moving on, here is the disk. Here is the electric field right at the surface. Now, again, textbooks go back and call this an infinite plane of charge. I don't like that because there's no such thing. So, an infinite plane of charge doesn't mean there's an infinite plane of charge. An infinite plane of charge means that in the limit, as x approaches 0, any finite disk of charge will look infinite. It's kind of like the surface of the Earth, right? If you look at the surface of the Earth, we're so close against the surface, you look out and you go, oh my gosh, it's infinite. Land just goes on forever and ever. But if you step back, you go, oh, it was a sphere. It looked like it was an infinite plane, but it was really a sphere. In this case, when you get really, really close, it looks like an infinite plane. But when you step back, you go, oh, it's just a circular disk. I thought it was an infinite plane. So I just want to be clear, that's always was a confusing, always created a mental block for me when they would talk about infinite planes of charge. Again, I don't think that's the way to think about it. Think of, I'm really, really close to a finite disk of charge, so close that it looks infinite to me. Okay, I hope that helps. Now, they use the same diagram here, but I think it's wrong. So we actually have to take two of these. In this example, what they're going to say is, let's take two of these. I'm going to move on and place them next to each other. If we're in a region between these two plates, then what would the E field be? Now, what they're going to claim is that, well, in this problem they said one of these plates, again, I'm going to imagine two circular disks. So I got two circular disks. Did they call this an infinite plane? They didn't. They called them circular disks. So here's a circular disk here, here's a circular disk here, they're side views. This one, in this particular problem, this one is positive, this one's negative. Now, we're going to be seeing this kind of configuration pretty often. This is considered a way to generate a uniform electric field. So we use kind of this picture or this diagram to claim that it's a uniform electric field. It turns out it's not as simple as this, but let's take a look. If I'm at a point between the two plates, the claim is that I'm close enough to this plate that I can use the approximation 2 pi k sigma. And I'm close enough to this plate that I can use the approximation 2 pi k sigma. I can treat it as if I'm right up against both of the plates. Well, that's not true unless the distance between the two plates is really, really small compared with their radius or with their diameter. So I would have to, in order for this to be a useful approximation, I would have to have the plates be very close to each other in order to use the formula 2 pi k sigma. Now, if I'm in the region between the two plates then, 2 pi k sigma plus 2 pi k sigma, they both have the same surface charge. One is positive, one is negative. I would combine those two E fields because the positive plate has an E field directed away, the negative plate has an E field directed towards the negative plate. They reinforce each other, and the E field between those two plates then would be 4 pi k sigma. What happens if I move to a point outside? If I move to a point outside and still want to use this approximation, then point B would have to be really close to both of the plates. So the plates would have to be really close to each other, and the point outside would have to be really close to that plate. But these examples are commonly used. You'll see these in the textbook. You'll see these probably in some of the homework problems. So in this case, what we do is we say, this plate, the positive plate's creating an E1. Even though the negative plate is in between, we still get an E field effect. So it's not like one of the plates cancels out the other plate. We want to include the effects of both plates. So the E field from the positive plate, we still have to consider that. The E field from the negative plate, we still have to consider that. Now here's where the approximation kind of breaks down. We assume that since this point is so close to both of the plates, that both contributions are the same magnitude, 2 pi k sigma. Therefore, the electric field outside of the plates will be 0. And that's only going to work if the two plates are really, really close to each other. Only if the plates are really close are we going to get a cancellation that gives us something close to 0. So realize these approximations are sort of limited usefulness, but we're going to use them. So we're going to use them over and over and over. Just remember that this really only works if the distance between is small compared to the area of the plates. Okay, so our approximation is that's going to become kind of a standard way that we generate a uniform electric field. All right, field lines. Let's talk about this a bit. We've drawn these pictures before and said that what they're useful for is identifying orientations of electric fields at different points. There's actually kind of a list of rules where we can go in and draw a bunch of field lines and estimate the strength and directions of electric fields without doing any math. Now the rules look like this. It says that the lines have to start at the surface of the charge. The lines are directed perpendicularly away from the charge. So see how those lines are directed away perpendicularly, and that the number of lines is proportional to the charge. So I know these two charges have the same magnitude because they both have the same number of field lines drawn. And then what we can say is that as the field lines begin to spread out, the E field is not as strong. The density of the field lines tells us how strong the electric field is, and the density of E field lines is highest near the charges, and it drops off with distance. So here are those rules. Now here's a situation that is useful. It's called an electric dipole. It consists of a positive and a negative charge, both of the same magnitude, that are, for some reason, attached to each other. So there could be a mechanical attachment. This end is positively charged, this is negatively charged. Something is holding them together. Since they're the same magnitude charge, we're going to use the same number of field lines. Now, the field lines surrounding a positive charge are directed away from the surface. The field lines around a negative charge are directed towards the surface. Both need to be perpendicular as they approach or as they are directed away from the charges. Now, since we have the same number of fields, since these charges are the same, it says that the field line from the positive charge will, if we follow those and draw them, all terminate on the negative charge. Now remember, there's nothing actually moving in this direction. We could just as easily define the electric field in the opposite direction. This is just a handy way to keep track of what happens if a positive charge comes by. But what this allows us to do is, without doing any math, but just drawing kind of these curved effects, and eventually these lines come back and attach, is we have an idea of how the E field is directed. So it says that for a dipole, right at that point, the electric field is tangent to these field lines that we've drawn. So the field lines are continuous. The E fields are values at particular locations. Now on this one, they drew one line that just continues out to infinity in this direction, and they drew another line that continues out to infinity in the other direction. And that's true. If you stay right on the axis, you're going to have E fields directed. The E field lines are spreading out, which means out here the E field is weaker. In here where it's concentrated, the E field is stronger. So it's an interesting technique. Now, here is our approximately formula with the two charged surfaces, remember. The electric field between two closely spaced, oppositely charged parallel plates is approximately constant. Now, they even did a few squiggles here. These last couple E field lines are squiggles because there are what we call edge effects. If you stay away from the edges, the E field is pretty uniform, but as you get closer to the edges, E field is going to drop off. So again, here are the rules that we talked about with those field lines. And I think we went over all these. So I am going to move on. Now, how do we follow these electric field lines when we have a conductor? So if I have a conducting piece of material, something that's a metal, for example, let's imagine we have a metal sphere, and the metal sphere is hollow, but somehow I've placed a positive charge inside. So I got a positive charge, there's a little opening, there's a door on my metal sphere, I open it up, there's some structure inside where I can place a positive charge, close the door, and here is the positive charge inside. Well, the electric field lines are going to spread out uniformly from that positive charge. When they get to the conductor, they have to stop. Conductors will not support an electric field, and here is why. Here is the reasoning. If within a conductor there were an electric field, the electrons would begin to move, and the electrons will continue to move until the electric field goes away. So conductors are moving targets for sure, in that I can't take charges and tell them how to stay. The charges in a conductor will rearrange themselves until the electric field goes to zero, and then they'll stop rearranging themselves, and the electric field will remain zero. So I can temporarily create an electric field inside a conductor, but very quickly the electrons will respond to that. So what that says is if I place the charge inside here, electrons will be drawn to this surface because there's an electric field temporarily, and then once the electrons are in there, those electrons terminate the field lines. And so the electric field lines don't continue through the conductor. Since there's been a group of electrons that have now been pulled towards that inner surface, that leaves the rest of the conductor somewhat positive. And in particular, we'll see this in the next chapter, we can show that in order to maintain zero E field inside the conductor, what happens is there's going to be a positive charge established on the outer surface. So the inner surface becomes negatively charged, the outer surface becomes positively charged. There's no E field at all within the conductor itself. The inner surface will end up with a charge of minus Q spread around the inner surface. That will exactly cancel the E field lines from the plus Q. And then on the outer surface, there will be a total charge of plus Q because the conductor itself has no net charge. If a charge of negative Q goes to the inner surface, that's going to leave a charge of plus Q on the outer surface, and the E field lines will continue. Okay, so conductors with E field lines is kind of an interesting situation. Here's another feature of conductors. Conductors cannot sustain an E field along their surface. An E field that runs tangentially to the surface would result in electrons moving. So again, the electrons or whatever charges are along the surface, those are going to keep moving until the lateral E fields cancel out, and all we're left with is this perpendicular E field directed away from the surface. So for a conductor, the E fields have got to be directed perpendicular to the surface. We can't have any components of the E field along the surface. So here's a conceptual example. Let's say that we have these plates, positive and negative. We're going to generate an electric field. What we're going to do is take a metal box inside here with an opening inside, and we're going to charge these plates. We're going to show the E field lines. So here are the E field lines. Remember the squiggles on the edge effect. What's going to happen with that inner conductor is that the E field lines are going to run right up to the conductor, but the electrons in the conductor will rearrange themselves so that the E fields cancel out. Now what that does, if I have a hollow region inside, is that hollow region is going to be, in some sense, protected. There won't be any E field lines inside there. So this is kind of like driving in a lightning storm, right? The lightning storm, here is the Earth negatively charged, here are the clouds positively charged, or vice versa, one or the other. And a bolt of lightning crosses between these two plates. You're driving along in the car, what happens? You're fine. Okay, the electric fields, there's enough electrons in the metal box that you're in that the electric fields are canceled out by those moving electrons. The electrons respond quickly enough, I hope, I guess I'm thinking with lightning this happens fast enough, that the contents inside that metal box don't experience that large electric field. All right, we're moving on to another really important topic. So chapter 21 just goes on and on and on. We talked about that, but there's a number of really important topics in here. We want to ask what happens to a charged particle, maybe an electron, maybe a proton, placed in an electric field. Now, the force acting on a charge in an electric field is Q times E. So we've used this before. I don't know if we've emphasized it enough. I should have put a little yellow box around this one too. That's a really important formula. Let's see what effect that has. So I've got this parallel plate set up, and we're imagining that the parallel plates are generating an electric field. Now for an electron, what we want to do to accelerate an electron, we want to speed up, we want to generate an electron beam. And so I'm going to start with electrons at rest along one of the plates, and then the electron will be pushed away from this plate and drawn toward the positive plate. And just when the electron gets close to the positive plate, the electron looks out and sees that there's an opening. We've actually made a hole in that plate, and the electron is going super fast, and it goes right through the opening. Now, if we think back to the electric fields surrounding these parallel plates, what's going to happen is there's going to be a force acting on the electron all the way across the region between the plates. Once it gets outside the plates, the electric field drops off to 0, is our approximation. So it's going to pick up speed between the plates. Once it exits, it's just going to cruise at some constant velocity. So what this is saying is, okay, here's the electron, there's its mass. Here is the electric field. Let's say we've generated an electric field of 20,000 newtons per coulomb between the plates. The plates are separated by 1.5 centimeters, and the electron then would be accelerated from rest near the negative plate, pass through the tiny hole. What speed will the electron be traveling with when it exits? Now it says show that the gravitational force can be ignored, so we'll see how that shows up in the calculations. Assume that the opening is so small, assume that we still maintain a uniform electric field. So we're fine with that. All right, here are the plates, here's the electron. Notice the electron is moving opposite the electric field because the electron's negative. The force on the electron is going to be to the right, the field is going to be to the left. The electric field magnitude, 20,000 newtons per coulomb. The distance, x, 1.5 centimeters. I wanted to go in and look at the acceleration here. I was just curious. And so, actually, we need to do that to solve the problem. The acceleration here is force over mass. Now, the force comes from taking that charge and multiplying by that electric field. Now, that's an enormous electric field, 20,000 newtons per coulomb, but that's a tiny, tiny, tiny charge, 10 to the minus 19. So the force here is really tiny. This is like 10 to the fourth, this is like, it's like 10 to the minus, you know, it's like a trillionth of a newton. But it's an electron. So the electron has a tiny mass. When we take our tiny force and divide through by the tiny, 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 really tiny mass, we get an enormous acceleration. We saw this before. We suggested not to worry. Accelerations can be really, really large in these examples. So the acceleration worked out 3.51, 10 to the 15 meters per second squared. And if the E field is constant, then the force is constant, then the acceleration is constant. And that's good news because back in Physics 4A, we had developed, in the kinematics chapters, formulas for constant acceleration. If we have constant acceleration going on, we have formulas like this. So I pulled out the formula for velocity as a function of distance. Now, I should have done the other ones too. You guys could try this. So there's some other interesting questions here. One would be, how much time does it take for the electron to cross from one side to the other? That would be a good homework problem to take a look at. Another problem we could ask about is, no, I guess that's it. So time, distance, velocity. So the distance was given, and we're now solving for velocity. And I used this formula. Now, the initial speed is 0. And so I went through solve for the speed. The speed we get up to is 1.03, 10 to the 7th meters per second. So that's quite an amazing acceleration. We've got a distance of 1.5 centimeters, you know, something like that. And at one of the plates, the electron is at rest. By the time it gets to the other side, it is going at 3.4% of the speed of light. And 3.4% is slow enough that we can keep using the formulas. We don't need special relativity. We can use the formulas from Physics 4A. They're going to be pretty reliable at 3% of c is the speed of light. 3 times 10 to the 8th meters per second. So that's not unusual. When we generate beams of particles in different devices, we can bring these electrons up to speed over really, really short distances. All right, just for comparison, I wanted to throw in protons. I always feel like if you do one, you got to look at the other. So same numbers, 20,000 newtons per coulomb for the electric field, 1.5 centimeters, starting from rest. I had to switch the plates, or I had to switch the charge. So whatever source I had attached these plates to charge them, I have to switch them. This now is going to be the positive plate, that's going to be the negative plate, because the protons are positive, and I want to have the proton getting accelerated out of the plate region. Now, let's ask some questions. Same formulas. The only difference here is the mass of the proton is not the mass of the electron. In fact, the mass of the proton is going to be 1,800 times larger than the mass of the electron. So, looking at our formulas, the force is going to be the same. The charge on the proton, same as the charge on the electron. E field is the same. So the 3.20, 10 to the minus 19 newtons, that's the same as the electron. At that step, the proton and the electron, it's the same amount of force. It's when we get to the acceleration that things change. The acceleration depends not just on the force, but how much mass, how heavy is that object. And the proton is 1,800 times heavier. So its acceleration will be 1,800 times smaller. It's going to be 1/1800th, roughly, of the acceleration for the electron. I'm going to use the same constant acceleration formula. It says that the proton is only going to acquire a speed of 240,000 meters per second, or 0.000799 times the speed of light. So, you know, less than 1% of the speed of light, like 0.00, less than 0.1%. Let me say that, less than 1,000th of the speed of light. Okay, good to think about that comparison. It's always the mass of the proton. The difference in masses that makes a difference. Let's look at another example. These two examples are really good, both of them. That first one, just accelerating an electron or a proton in one direction. This time, we're going to start with an electron entering an E field region, but it's going to enter it with an initial velocity, and then it's going to get pushed sideways. So this is kind of like projectile motion. Remember when we, in Physics 4a, when we threw objects horizontally off a cliff, what was their trajectory like? And you go, okay, they're going to have an initial velocity in the x direction that's constant. And then the force, there's going to be a downward force that begins to accelerate the electron in the negative y direction. Now the E field is oriented positive because they're electrons and we need to have the force on the electron be downward. Here's the picture. Here is the diagram of all the directions. And I went through and calculated what the acceleration would be. Now this acceleration is in the downwards direction. Remember, the velocity, there's an initial velocity of 1.0, 10 to the 7th meters per second in the x direction. And that's going to be maintained. And so I went through and calculated the downwards acceleration. The velocity in the x direction is just going to be 1 times 10 to the 7th meters per second. Velocity in the y direction will increase with time. So I was kind of curious. I always add things on these problems. I wondered what would happen once a little time had gone by. And so what I imagined was, well, if it's 1.0, down here, if the acceleration is 10 to the 15th meters per second squared, what would happen after 1 nanosecond? Now, 1 nanosecond multiplied by this acceleration says that, well, the Vx hasn't changed, but the Vy now is 3.5 10 to the 6th meters per second. And again, I use some more formulas from constant acceleration, from kinematics, and ask myself, well, after 1 nanosecond, where would this electron be located? You know, it's going to follow this parabolic path. And plugging into the formulas, I got in the x direction, it will have traveled 1 centimeter. So that's kind of useful. After 1 nanosecond, 1 billionth of a second, this electron has traveled horizontally by 1 centimeter. In the y direction, I have to use the acceleration formula 1/2 at squared. I put those numbers in, and it said that y would be 0.0018 meters, and then I converted it into millimeters. So in the x direction, after 1 nanosecond, the electron has traveled 10 millimeters. In the y direction, it will have curved and will now be located below the horizontal, 1.8 millimeters. So 10 millimeters horizontally, 1.8 millimeter vertically, and at that point, the Vx and Vy components are given here. So I wanted to make this look as much like a kinematics problem, a projectile motion problem. These are useful problems. Make sure you look at these examples. There's always this chapter fatigue. You know, you start off chapters, at least I do, start off chapters enthusiastic, thinking, yes, it's a fresh start. I'm going to get this chapter. I'm going to understand everything. And then as the chapter progresses, it gets harder and harder to maintain that enthusiasm. And chapter 21, the one we're looking at right now, has so much stuff in it. It's easy for chapter fatigue to set in. So make sure you get a fresh start, several fresh starts on this chapter. You know, maybe read the first few seconds and you start, and then come back some other day and read the next couple. Anyway, this is an important section. Make sure that you look at these two examples. All right. Did I mention make sure you look at these two examples? Okay. It's a good chance to review kinematics. All right, electric dipoles. We had looked at some, and I think this is kind of the last major section, so we're going to be wrapping this up here. But we're going to come back and look at these electric dipoles. We saw this in one of our examples. Just as a review, an electric dipole consists of some amount of negative charge and some amount of positive charge that for some reason are attached. They're stuck with each other. They don't come together and collapse, and they don't get pulled apart. They maintain some kind of a distance. Now, how could this be created? We could make a mechanical device. We could just build something, right? Maybe we get a piece of a stick, a piece of wood or something, and we get some kind of a conductor on each end, and we charge them up. And one end is positive and one end is negative. But the charges are fixed at a certain distance, L. Well, that would be a dipole. The other place that we saw dipoles, and we'll get to this, I've got some pictures ahead, were when we looked at molecules. Remember when we talked about atoms way back at the beginning of the chapter? It was like weeks ago or something like that. We looked at the water molecule, and we said that one end is kind of positive and one end is kind of negative because of the way the electrons arrange themselves around the nuclei. Well, that's a dipole. So separation of positive and negative charge creates a dipole. Overall, the dipole is neutral, but there's a charge separation, and that means that it will have an effect on its surroundings. The positive and negative charge effects won't cancel out. So mechanical devices or atoms and molecules are where we're going to see applications for these dipoles. Now let's see what happens to a dipole in a uniform electric field. So let's say we have an E field, it's uniform, it's the same value everywhere, the same orientation. That says that the positive charge and the negative charge will experience identical forces. Now they're going to be in opposite directions. The positive charge is going to experience a force in the direction of the E field, and that'll be Q times E. The negative charge will experience a force opposite the direction of the E field, and that will be Q times E in the opposite direction. That says that if we look at the net force of a dipole in a uniform electric field, we'll come back and ask what happens if the E field is not uniform. But in a uniform electric field, the dipole will experience zero net force. It's getting pulled forward, equally pulled back, so there's no net force. Now, even though there's no force, there's a torque. So a dipole, depending on how it's oriented, will experience a torque tending to rotate it so that the dipole orients itself with the electric field. Now, in this previous picture, we used a symbol P as a symbol to represent how much dipole do we have. Now it seems a little funny to define a vector for the dipole, but it turns out it's useful. Mathematically we know this. We know that everything we define in physics has to be either a scalar or a vector or what are called tensors. They're more complicated vector. They're like matrices. And so the dipole turns out to have directionality to it, and it can be represented as a vector. Now, the way we represent it as a vector quantity is to say it has a magnitude, and we define the magnitude as q times the length. Now, q is the amount of positive charge. It's also the amount of negative charge, each one individually. So q times L tells us how much dipole we have. And then the direction is defined as pointing away from the negative charge towards the positive q. Now that's opposite to how we defined electric fields, but there's a reason for defining it that way. If we look at the torque acting on this, what the torque is trying to do, okay, I shouldn't say try, but what's happening to the object is the torque is rotating it so that the dipole direction will align with the E field direction. If I take a dipole and place it so that it lines up with the E field, there's zero torque and it just remains stable within that electric field. If I place it exactly opposite the electric field, it's metastable. It's an unstable equilibrium, so that if it begins to rotate a little bit, the torque will continue to rotate it around. So, these pose interesting possibilities for creating something that rotates in an electric field. So here is the dipole. They wanted us to come in and derive formulas for the torque. So you guys remember torque, right? From Physics 4A, torque, kind of the rotational version of a force, something that tends to rotate an object. So here's that very same picture that we looked at. The force for each of these charges is Q times E, the magnitude. So the forces cancel out, but the torques do not. And I drew an expanded diagram here to calculate the torque, specifically identifying how much lever distance do we have for each of these forces. So the lever distance on this side is R1 times the sine of theta, where theta is the angle, theta is defined as the angle between the electric field and the orientation of the dipole. So again, we've defined both of these as vectors, and so we can define an angle between those two vector quantities. So torque 1, R1 F1 sine theta, torque 2, R2 F2 sine theta. The forces are the same, so these can be written as RQE sine theta. Everything matches except possibly R1 and R2, but we'll see, we're going to combine those in any case. So these two torques are working together. And what I mean by working together is they're rotating the object in the same direction. So I can add the torques together, and that means that I want to combine R1 and R2. When I combine those together, you know what they are? They're the length of the dipole. So it doesn't matter where I place the axis of rotation, I can place it anywhere, and R1 and R2, the combined lever distances, always combine to be the length of the dipole. So remember our definition, dipole is the amount of charge times the length, so we can substitute that in. And what that says is the torque we will get is PE sine theta. So it depends on the amount of dipole times the strength, or the amount of E field, multiplied by the sine of theta. So if theta is 0, they're aligned, there's no torque. Where is the maximum torque going to occur? And the maximum torque would be if I rotate the dipole so that it's at 90 degrees. That's where the lever distances are as large as possible. So the maximum torque I would get is P times E. Now we said, since everything has to be representable in physics as a scalar or a vector, and I can already identify in here, well, E is a vector and torque is a vector, and in fact, dipole we've defined as a vector. Is there a way I could turn that into a vector equation? And there's really only two options. There's the dot product and there's the cross product. And it turns out that this is the cross product. There's a factor of sign here, which corresponds to the magnitude of a cross product. And torques, remember, are going to be defined perpendicular to both the E field and the dipole. So the E field direction is in the plane of the paper. The dipole direction is in the plane. If I use a right-hand rule to do a cross product of P and E, I'm going to get something that rotates this object in the direction right. So if I do a cross, I'm doing a cross product with my hand. So P would be my thumbs, E would be my fingers, and the direction of my palm would be the direction of the torque. So the torque here is into the page, and again, using the definition of positive and negative directions for that torque, it's going to tend to rotate it in this direction. So yeah, I can define all three of these as vectors and write down a vector formula. Now, in practical terms, this looks cool. This impresses your friends. Yeah, it's this vector formula. But in practical terms, we almost always find ourselves coming back to here or breaking this down into components. We don't necessarily solve directly from the cross product formula. So let's look at a couple of examples of E fields due to the dipoles. In the previous example, we were saying, okay, if there's an electric field, how does the dipole respond? This time we're asking, let's just look at the dipole and ask, what does the E field do to the dipole itself? Because the dipole is going to create its own E field, and that could have effects on charges that wander by. So here's the negative charge, here's the positive charge. These are now written as L over 2 so that we can define a center of a coordinate system at the location halfway of the two charges, and that's a standard coordinate system setup. And now what we're asking is, if we come out along the y-axis to point P, what will the electric field due to those two charges, due to the dipole, what will that look like? And in particular, they want to show that the field behaves like 1 over r cubed. Remember, an individual point charge, the field drops off like 1 over r squared. So for a dipole, if I put equal amounts of positive and negative charge near each other, but not so they completely cancel, I'm going to get some cancellation of the electric fields, but not all of it. And it works out that for a dipole, that partial cancellation but not complete means that the E field now drops off faster, 1 over r cubed, instead of 1 over r squared. Now, for the dipole, in this example, we've got an E field directed away from the positive charge and an E field directed towards the negative charge at point P. Those are symmetric because of the equal magnitudes of the distances in the charge and the way that we have centered the coordinate system on the dipole. And that means that the E field is going to be directed sideways, which is kind of interesting. It's not directed towards the charges or away. It's kind of directed sideways. Okay, so let's go in and take a look at this. Now, instead of L over 2, a lot of times it's easier to go in and call this A and this A, and that means that the dipole now is Q times 2A. And then, oh, this is a different problem. That's right. This is a different example. So I'm not looking at a point here. I'm looking at a point on the x-axis itself. And so I'm defining a distance from the center of the dipole out to point A, and I'm getting an electric field contribution from the positive charge, that's E1, and I'm getting an electric field contribution from the negative charge, that's E2. And so I wrote down the formula for the E field due to a point charge for charge 1 and charge 2. Now, I put the minus sign in here right now just to point out that it's in the opposite direction. And then I'll add the two E fields together. I do, from the diagram, have to keep track of directions somehow, and that's how I chose to take care of it in this problem. Notice that the E field 1 is going to be bigger than E field 2. So again, we want to look at the diagram first and make predictions before we start to derive formulas or plug things in. And what I'm seeing is that since the distance to the positive charge is shorter, E1 will be bigger than E2. So E1, the distance out to point A, is x minus A, so that gets squared. But for the negative charge, it's x plus A. So I'm adding these two E fields, or taking the difference between them. That's a square sign. And then I carried out the algebra here. The A's canceled. The A squareds canceled. The x squareds canceled. But the 2ax cross terms did not cancel. They added together. So far we still have an exact expression for the E field along the axis. And what this is telling us, here is, I should have boxed this one. This is a nice place to stop and stare. Notice that if I came to point B over here, the E field would still be in this direction, everywhere along the x-axis, except for between the two charges. The E fields are going to be directed in the positive direction. Now, we wanted to establish this 1 over r cubed effect, so let's try that. If x gets really big here, compared with A, then I can ignore A squared because it's just added or subtracted. And that becomes x squared squared, which is x to the 4th, and that will cancel one of the powers of x and leave x to the 3rd below. So there it is. There is the x cubed effect. And I guess that is it. So I ignored the a squared here and left x to the 4th. I did an arrangement here to show that the E field now is kind of like the E field for a point charge, k2 over x squared, but I've got a factor of 4, a factor of a over x. Now what I'm going to do is rewrite this in terms of not the charge, but the dipole. Now remember, the dipole in this example is q times 2a, so I factored those out and replaced them with a dipole. So the E field along the axis, 2k dipole over x to the 3rd, there is the r cubed expression. Now I'm going back and doing their example. I wanted to do an easier one first. So I did a little crazy thing here. Instead of calling this y, I called it x. I do better with x than I do with y. It sounds ridiculous maybe, but my failure rate with y is much higher. So I called this x. I did the same thing as before. What I did was showed that the two E field magnitudes, this time they're identical. The magnitudes are identical, but each one is going to pick up a factor of cosine theta. So the E field is directed parallel to the x-axis, and this is the magnitude. The sideways components cancel out. The cosine theta is a over a squared plus, so I'm just using a trig function here. That's my exact formula for the dipole along the y-axis, even though I wrote it in terms of x. Now again, what we can say is if a is really, really small, so when we talk about a dipole, we usually imagine these charges placed close together and we're measuring the field far away. So once we get far away from the dipole, we ignore the a squared and the formula becomes 2kqa over x to the 3rd. I replaced the q2a with the dipole. It becomes kp over x to the 3rd. Now that's 1 over distance cubed behavior. There's my dipole. In the earlier example, we identified E fields here, and now in this example, we're identifying E fields out to the sides. Okay, here's a problem. It's a water molecule We're going to treat this as a dipole. So they actually told us how much dipole. It's sometimes called a dipole moment because of the torque effect. Anyway, this is how much dipole a water molecule has. So first of all, I wanted to look at the water molecule and ask, what does that mean? So here's a water molecule. I looked up some numbers. It said in the water molecule, the bond length, this distance right here, is 95.84 picometers. I looked that up. That's the bond length between the nuclei for a water molecule. And the opening angle here is 100, and I didn't write those down. I may have a diagram that shows it that's coming up. 104 degrees, 105 degrees, so this is 52.5. Anyway, what I did was identified this distance right here is distance A. Now, if this is a dipole, then that's the distance between, I changed A so that it's the same thing as L. Sorry about that. But what I'm doing here is I'm solving for, given the length of the molecule, how much charge separation am I getting? And the water molecule, you can see it's pretty significant. The electrons, now there's a lot of electrons in water. There's 1 from each of the hydrogens and 8 from the oxygens. So we have 10 electrons total, right? And so of those 10 electron totals, the separation of charge is equivalent to about 65% of one of those charges. So it's effectively 65% of one electron got up from one side of the molecule and moved to the other. Now that's not really what happened. What happened is there's just a general shift in the charges. But if I calculate now the torque, I can use that formula. They said, what's the maximum torque that a water molecule would experience? Well, I can plug in the dipole that they gave me, the electric field, 20,000 newtons per coulomb. They wanted the maximum, so I used 90 degrees, sine of 90 is 1, and as you would expect, the torque is tiny, 10 to the minus 25 newton meters of torque. Okay, here is my water molecule. I guess I got these slides reversed. This would have been a good one to show before. So here is the water molecule. And then I also, so here's the other pictures of the water molecule. So here is the water molecule, there's the bond length, there is the angle between the two bonds. Now that's not what the atom looks like. This is what the atom looks like. So those represent electron distributions within the molecule. So the nuclei are little tiny point charges. So there's a little tiny point charge in the oxygen and little tiny point charges in the hydrogens, and then they're surrounded by these clouds of electrons. Now in water, what this positive and negative creates is a leftover attractive force. Even though we form the chemical bond of the H2O molecule, there are leftover positive and negative charges that create this effect of what's called hydrogen bonding. And that makes water a liquid. Now they ask also about potential energy. So the way potential energies in rotating this molecule, you could imagine if we line up the molecule so it's oriented with the electric field, and then we begin to exert a torque to kind of wind up the dipole within that electric field, that we can calculate the work or the energy required to rotate this dipole as torque integrated over angle. Now, work also was something that we looked at in Physics 4a. I think we briefly introduced the idea of instead of a force times a distance, it can be a torque times a rotational distance or a rotational displacement. And so that's what I've done here. I plugged in the formula for the torque and integrated from some angle out to pi over 2. So what I'm doing is asking if I start at an angle theta and rotate this out to pi over 2, how much energy would that require? And I ended up with this formula of P times E times the cosine of theta. Now, if it requires a certain amount of work to rotate this, that becomes a potential energy. So I've rotated the molecule and stored up a certain amount of potential energy. If I now let go, I can get the energy back in this dipole. It could be a molecule or it could be a mechanical device that we've designed. So what we can do then is define the potential energy as the negative of the work. Being done by the field. And so the potential energy that we store up is negative PE times the cosine of theta. Here is the plot for that. And we can write this as a dot product. So the torque we could write as a cross product. The potential energy we can write as a dot product. All right. One last example. I know we're getting to where we should wrap things up for the day. Chapter 21 does go on and on. I'm going to go through this quickly. It's something you're not required to do. You're certainly not responsible for this on an exam. But what we're looking at is if I have two dipoles, how do they exert forces on each other? And it's complicated. Depending on the orientations of the dipole. So I picked what is, I guess, the simplest orientation. I picked up the dipoles so that they're right along the x-axis. They could be tipped at different angles. And wrote down this expression. So I wrote down there's 4 interactions taking place. The positive and positive are repelling each other. The negative and negative are repelling each other. This positive is attracting that negative, and this negative is attracting this positive. So I wrote down those 4 forces all together, and then I factored out a factor of 1 over r squared. I was left with this. We had looked at approximation techniques earlier, and so I used that very same formula. Now, in this case, when I approximated, I can take the 1s and then the next term. It turns out in this particular example, not only do the 1s cancel out, but the next term cancels out. I have to keep one more term in my expression. So if you're like me, you're thinking, oh my gosh, I got to keep another term in this series that I'm writing down for the function. We had to move on to the next term in the series. I used those, plugged those in, and was able to show that everything cancels up to those terms. The force that I get between 2 dipoles is like 1 over r to the 4th. So remember, the force between 2 point charges is like 1 over r squared. But because the dipoles have this cancellation effect kind of built in, the forces drop off pretty rapidly. Now that would represent forces between water molecules, hydrogen bonding, right? So hydrogen bonding drops off probably like 1 over r to the 4th. It's a more rapid drop-off than we would have imagined. One of the places where hydrogen bonding becomes really, it's very important in all of molecular biology. So many of the molecular biological molecules, proteins, DNA, and such, depend on these dipole-dipole interactions between different parts of the molecule. In DNA, where that shows up is between the bases adenine and thymine and cytosine and guanine. So here is a DNA double helix, and there are hydrogen bonds which occur stepwise through the DNA molecule and hold the molecule together. Here's a close-up of the 4 different compounds involved. Adenine lines up with thymine, and there's a pair of hydrogen bonds taking place between those two compounds, between those two molecules. Cytosine and guanine have alternating hydrogen bonding taking place at 3 locations. And so what happens during DNA replication, or RNA formation, is that the A's and T's and C's and G's are generated within a cell metabolically. Your cells continue producing these different nucleotides, and when DNA replication takes place, the molecules are very selective about which base goes with which base. And so the DNA is able to accurately maintain the series of A, C, G's, and T's, and that's what maintains the genetic code within DNA. This is based on hydrogen molecules. I'm going to go back to here and say that's the end. There's some stuff on printers. I'm not worried about that. But anyway, this to me is a pretty cool place to kind of wrap this up. And just a reminder that in chemistry, we talk about chemical bonds. That's the biggest effect of the electric force. But there are these leftover electric force effects, like hydrogen bonding, that become very important in many situations. And biological molecules is one of the places this shows up and maintains a high level of specificity for these interactions. Make sure that the correct molecules line up with other molecules. All right. Ooh, thanks for letting me go over a little bit. Sorry about that. Even with 4 lectures, right? It was tough to fit all of chapter 21 in. But we are wrapping things up now. If you've got any questions, stop by.